the present electrical form. I'm also going to try to attempt to show the part that amateur radio played in both halves of this, the center being 1919. The first attempt to overcome distance by electrical means started in the 18th century with Leyden jars and long stretches of chain or wet string, Benjamin Franklin being one of these people. When Volta discovered the electrical pile and was capable of producing direct current, that opened the way for the experiments of Faraday and Henry in developing the electromagnetic telegraph. This development inspired the search for a wireless telegraph. With the advent of the Edison and Tesla power systems, the implement for wireless furthered. The declaration of Maxwell that electricity and light were analogous laid the groundwork, and Tesla's development of alternating and oscillating current devices naturally led to the electric wireless. Tesla was more interested in wireless power than wireless telegraph, that is, the wireless transmission of electricity. This led to far different results from those of Hertz and Marconi. Amateur radio played a part in the experimental development but was shut down in the massive global readjustment program following 1913. Free communications was not in the plan. Marconi stations such as KPH in Bolinas, California were seized, and RCA took over and eliminated the Marconi system, fashioned on Tesla's ideas. Following RCA's formation, amateur radio was restored and given the worthless frequencies above 1,500 kilocycles. Hams found that these frequencies allowed for very long distance but intermittent transmission by Hertzian means. RCA grabbed onto these frequencies and established electromagnetic radio. The Tesla-Marconi system was forever abandoned. The present amateur radio has abandoned all experimentation and has embraced the corporate instituted technologies of the New Babylon. Although amateur radio has the potential for the development of the Tesla non-electromagnetic radio system, the lure of the 2-meter yak-yak renders this development unlikely. In all likelihood, Tesla's important developments are lost forever. But let's see what's going on here. We track the history of, see if we can get this to spin, history of wireless communications. It started with a person by the name of Matthew Loomis. What Loomis did is he chose two mountaintops 6 miles apart and flew two kites up into the atmosphere, roughly about 1,000 feet up. As you can see in the diagram, he hooked the telegraph key to one and a sensitive galvanometer to the other. And sure enough, when the key was hit on the other end, the galvanometer moved on the other end, and Morse code transmission was possible. You also notice that there's no battery, no Southern California Edison, no Pacific Gas and Electric. Edison tried to develop a form of wireless where trains with long wires stretched along them could communicate to the telegraph wires along the tracks, this being a magnetic system and very ineffective. Basically, these could be called single energy forms of transmission, and this one uses pure electrostatic, and this one uses pure magnetic. It's interesting to note that the electrostatic worked and the magnetic didn't. Then we move on to the double energy wireless, where the real progress was made. Hertz in 1880 found that he could transmit VHF and UHF signals by discharging a capacitor into a loop, a half-wave loop, and a half-wave loop at the other end would produce a spark. But this didn't work over a very great distance. Tesla found by taking two resonant coils and exciting one with alternating current would produce the appearance of electrical power at the other end. This worked at very far distances, and no RF amplifiers were required. It wouldn't light up a light bulb at the other end. As wireless progressed, Tesla established the system where he could transmit longitudinally through the Earth electrical power at a velocity of 291,000 miles per second. Also, he developed a beam tube.
What was that speed?
291,000 miles per second, pi over 2 times the velocity of light.
186,000 miles per second is C. I think you're exceeding C. Maybe kilometers?
No, it's pi over 2 times the velocity of light.
He is exceeding C. He'll go on and explain.
Okay.
There's a different set of dimensions.
All right.
Velocity of light simply is an expression of the ratio of energy to mass.
All right, which is a limit.
A limit to what?
As a constant.
It's a constant,
Yeah.
not a limit. In the beam, Tesla found that he could transmit direct current energy over incredible distances. And this energy not diverging out of the beam, much tighter and more compact than any laser ever built. In the longitudinal mode through the ground, there is really no losses, and the light bulb would light up at the other end. Marconi, in an attempt to circumvent the Tesla patents, changed the impedance of the system and used the flat top antenna, where you would get transverse electromagnetic propagations at 186,000 miles per second and longitudinal magnetic dielectric transmissions at 291,000 miles per second. For those that want to go back through history, Professor Wheatstone proclaimed that the velocity of electrostatic induction was pi over 2 times the velocity of light. As those of you that know about electronics and electricity, I'm sure you've all heard of the Wheatstone Bridge. Wheatstone was a very important researcher. As things progressed, we ended up with this. Thanks to Mr. Sarnoff and RCA, all of these things were eliminated, and we ended up with a system where transmission only propagated at 186,282 miles per second. And the losses in the system were total. This occurred in 1919, and by then Tesla vanished from the scene. Now, if we analyze these systems, we find that the longitudinal magnetodielectric system, that the electrostatic lines of force and the magnetic lines of force are directed in the same axis as the propagation of the electrical energy. In the Hertzian system, the magnetic lines of force and the electrostatic lines of force exist at right angles to the direction of electrical energy propagation, and this is what accounts for its incredible losses. In this system, we have little or no losses. In this system, we have an extremely high level of losses. In fact, by its very definition, it's resistance. It's called radiation resistance, a term familiar to many. Now, also, we have the waveforms that these devices produced. Now, we're familiar with the conventional alternating current. Okay, the alternating current has a real frequency in cycles per second. And it constantly cycles in a circular fashion back and forth. And then, of course, we know about the continuous current, or the direct current, which has no cycles per second. This would be called the scalar frequency. Scalar, by definition, is a quantity that does not vary in your system of variation, of either time or space or whatever variation you're talking about. Example would be like atmospheric pressure. Atmospheric pressure is the same everywhere in this room. And that's a scalar function. But if we take the function of the height of people in the room, obviously that's a spatial function. I can see all these waves moving around. So we have a scalar function, and then we have a regular function of variation in this dimension of space within this room. Now we have the waveforms that have become forgotten since the days of spark gap and wireless. One is the impulse wave, which is measured in decibels per second and has an exponential waveform. Where this waveform is expressed in sines and cosines, this waveform is expressed in hyperbolic sines and hyperbolic cosines, and never truly dampens out, but always approaches zero asymptotically. And then we have the oscillating current waveform, and this was the one utilized by Tesla. This waveform is expressed in cycle decibels per second. Now, in Tesla's time, he had a concept which he called individualization, where he would attune his resonant devices to respond not only to the cycles per second, but to the decibels per second, and produce a second order of tuning, where the waveform